So what does a transistor radio, AM/FM, a wireless router, and fiber optics all have in common? Stick around. We're going to discuss it and find out. Hey, this is Keith, Vantech Consulting. So the question, what do all of these devices have in common? Wireless router, radio, fiber optics. Answer simple. Frequencies. They all use frequencies to transmit their information. So the wireless router uses 2.4 gigahertz and 5 gigahertz spectrum, breaks that into channels, and uses that to transmit information to your cell phone, to your computer, to your television, whatever you got connected to it. The radio and the FM and the AM have different frequencies to broadcast information to us. And we use a tuner as a filter, and that filter narrows down and selects one specific frequency so we get that information. So talk radio, country music, classical. And it's the same thing with your satellite radio. You're tuning into specific channels, and those channels are specific frequencies that are carrying information to you. Fiber optics uses the same thing. Now, we don't call them frequencies, but they are. They're wavelengths, all right? And so we use specific wavelengths to carry information. So let's get into what a wavelength is and how it affects us in fiber optics. So when we look at this pulse of light, it's made up of multiple waves as it oscillates positive to negative and through zero. So it starts here at zero, and we can use degrees to describe this. So it starts at 0 degrees, it goes up to 90 degrees, it comes back down to 180, goes to 270 degrees, and back to 360 degrees /0 for the next wave. The distance between that oscillation, if you measure it peak to peak, so the point of the central point, or the peak of the waves, and this guy here, we're measuring at about 12.4 millimeters. And then if we went 0 to 0, we'd have the same measurement, 12.4 millimeters. So example, this is a 12 millimeter wavelength, right? Now in fiber optics, we use much smaller waves. So we're using 1310 or 1490, 1550, 1577, a lot of different wavelengths. Now that wavelength is, let's say 1310, is 1,310 nanometers, or 1,310 nanos of a meter. A nano of a meter is a 1/billionth of a meter. So this is pretty small wavelength. Now, one of the things that's important to keep in mind when we're talking about wavelengths is that the shorter the wavelength, so 1310, has a higher frequency than a longer wavelength, let's say 1550. So if we look at this guy, just to give you an example, we have 1, 2, 3, 4, 5, 6, 7. So we have a frequency of 7. Now, if we were to say, let's look at a half a second, and this was 7 in half a second, you can see that that has a higher frequency, right? So our frequency would be 14 over 1 second at this wavelength. If this spread out and became longer, then 5 would be our frequency. Longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency, okay? Now, why is this important? Because what do we know about frequencies? We know that the higher the frequency, the more attenuation we have, which is loss over distance. So the attenuation rate at 1310 is higher than the attenuation rate at 1550. And this applies to everything that we deal with. I mean, think about your Wi-Fi. So you've got 2 radios, or maybe 3 if you're using the current Wi-Fi standards. So we have 2.4 gigahertz spectrum, we have 5 gigahertz spectrum. Those are broken up into channels. So which one would get you to the workshop better? The workshop's out in your backyard somewhere, right? So the 2.4, it's in your router's in your office, so the 2.4 is going to penetrate walls and carry better. We don't have as much spectrum to carry information, but we get better penetration. The 5 gigahertz, it's a higher frequency, meaning that we have more space and more places to put information, but we don't get the carry, the penetration through walls and things. Think about, you're driving downtown, it's a nice winter morning, you got your windows rolled up in your car, you're snugly warm, snow's on the ground, all that fun stuff, and somebody pulls up next to you in their car and they want to share their music with you. So what do we hear? All we hear is the bass. We have no idea what they're playing in the car. They could be playing Mozart, they could be playing Beethoven, whatever, but the only thing that we can hear is the bass, because those lower frequencies carry better than the higher frequencies. The higher frequencies won't even make it out of the car. When we're dealing with wavelengths typically have a specific application. For most of us that are fiber techs, we're dealing with passive optical networking or some flavor of that. So either GPON, XGPON, XGS-PON, etc. So let's start with GPON. So GPON is gigabit passive optical networking. It utilizes 1310, 1490, and 1550. All right. So again, 1310, the shortest wavelength, has the highest frequency, a medium frequency, and a lower frequency. Okay. So the 1310 is the upstream. The 1490 is downstream data. And the 1550 is downstream, and we're going to call this RFOG. They define it as video, but it's RF over glass, which is utilizing the light and making it emulate analog video. Okay, so this guy here, 1550, typically isn't used anymore. So these guys here, if you're using IP data or IP video, or streaming, Hulu, YouTube, whatever, that's all coming across your data stream, your 1490. Our next wavelength, our next group of wavelengths is going to be in XG-PON. So the XG, this guy here is 10, right? So 10 gig PON, and it uses 1270 and 1577. So this again is the upstream, and this is the downstream data. So keep in mind that all 5 of these wavelengths would reside on the exact same fiber, right? So the equipment at the customer's house, the ONT or the ONU, whichever you choose to call it, it's the same thing. They're the ones that are doing the filtering, right? So think about what's going on here. Again, it's like this radio. These frequencies are hitting the antenna, and the filtering is done by this device, right? So that tuner is tuning it in and only allowing a specific frequency to come through. That's what the ONT and the ONU does. It transmits out, the XG-PON transmits its upstream requests at 1270. The GPON upstream request at 1310, it receives its data at 1490 and receives its data at 1577 on the XG-PON. All right. So again, they're all on the exact same fiber. Now, to make this even more fun, we have something coming out, or a standard for what's called NG-PON 2, and that is a 40 gig service, and it uses 4 wavelengths, so 4 by 10, to deliver the 40 gig. Those guys will also reside on this fiber, right? So now we're going to have 9 wavelengths traveling on here. The other thing that can happen on the same exact fiber is we can get wave division multiplexing going. And I think you can get something like 1, 2, 3, 4, 5, 6, 7, 8 wavelengths overlaid on the exact same fiber. So we were at 5, 9, 17 wavelengths going on here now. There's also a standard, wait for it, for 50 gig, right? That would be on the exact same thing. So you can deliver all these different flavors of passive optical networking to the customer on the exact same fiber. And how this looks is you have your equipment down here, and this is putting out the different technologies, the GPON, the XG, the NG, we'll call it kind of squishy here, 50. Okay, so we have our 4 technologies, or 5, whatever, and those are going into a mux, let's call it, a multiplexer, which muxes them down onto a single fiber. And at the far end, we have our 4 technologies, or our 4 fibers going out to our customers, right? And this ONT sitting at the end, your customer's modem, for lack of a better term, is the one that's doing the filter. So this guy here is getting we'll call this the NG, this is the XG, this is a GPON, this is 50 gig, whatever. So again, the devices down here are what are acting as that tuner and allowing only that wavelength through and utilizing only the information on that wavelength. So this isn't something that's, terribly new to it. The concept has been around. Our TVs, our radios, our Wi-Fi, our cell phones, or, all that wonderful fun stuff that we use every single day is the exact same concept that we're using in fiber optics. It's merely breaking up and using the different wavelengths as specific channels to carry specific information. I hope this clarifies for you what exactly the wavelengths are, how they're being utilized, and it's not really super scary. If you have any other questions you want clarification on, give us a comment. Be glad to answer it. We would like to send out a thanks to all the subscribers for support of the channel. We appreciate it. And until next time, be safe, and we'll see you on the next video. Thanks for watching.